Now we are going to state our main theorem, the inverse function theorem. So the situation is this. Omega is an open subset of Rn. And F is a map from omega to Rn, which is C1. Continuously differentiable. And A is a point in omega. So we consider the linearization of f at A. That is the derivative. So consider the derivative at this point A. So if this derivative, this is an n by n matrix. N by n matrix. If this matrix is invertible, the linearization is a very good approximation. The derivative is a very good approximation of our nonlinear map. Okay, so if this approximation is invertible, of course it is reasonable to expect that f is also invertible. Okay, this is quite reasonable. But the differentiability of f at the point A and the derivative here, f point A, depends only on the local behavior of f near A. Depends on how f behave in a neighborhood, in a small neighborhood of A. So, in other words, the invertibility assumption of the derivative is in fact a local condition near A. So you could not expect to determine the global behavior of f using only this local condition. So we can only expect that f is locally invertible. So this is not true. Local condition, local assumptions could not imply global conclusion. Therefore, you could not expect this to be true. You could not expect f to be invertible. But it is possible to expect that f is locally invertible. The exact, the correct result is that f is locally invertible. Okay, this is the inverse function theorem, the conclusion of the inverse function theorem. So to state this theorem and to simplify our language, we will introduce you some notation. So for a point in Rn, we use this Na. If you want to indicate the dimension, you also add a n here, denotes the family of open set. In Rn containing A. Okay, so we have this notation Na. For example, U belongs to Na means U is open and A is contained in U. Okay, so this is a notation. Next, we also want to introduce you diffeomorphism. Diffeomorphism. So let omega be a subset of Rn. A is an integral point of omega. Omega need not be open, but we require A to be an integral point. So a C1 map in omega to Rn. It is possible to map into another Euclidean space with different dimension m. This map is called a local diffeomorphism. At A. What this means? So this is omega. This is a map F, quite crazy. And A is a point here. And the image of F at A is B here. So when we call such an F a local diffeomorphism, the condition is that if there exists an open neighborhood of A, therefore in our notation we can write this, and another open neighborhood of B, that is another open set containing B. But these two families, NA and NB, are the family or the set of open set in Rn and Rm respectively. So to distinguish this, we might add a dimension here. So this will not will be clear. So U is an open subset in Rn containing A. V is an open subset in Rm containing B. So if we have such this pair of open sets containing A and B respectively, so that this map is bijective. It is 1, 2, and 1, 2, 1. And the inverse, because it is a bijective, it is 1, 2, and 1, 2, 1. So it has an inverse. And the inverse, that is a map from V to U, is also continuously differentiable. That is, we have an open set containing A and another open set containing B, such that restrict to U, F is a map. Consider F as a map from U to V. F is 1 to 1 and 1 to, that is, F is surjective. Moreover, since it is surjective, it has an inverse map, and the inverse map is also continuously differentiable. Okay, so if this condition are satisfied, then we say that F is a local diffeomorphism at the point A. Okay. Of course, you want to write, if you want to write this, because the domain of definition of F is omega, this implies that U must be a subset of omega. If part of U is outside omega, for point in that part, Fx has no meaning, because those x is not contained in the domain of definition of the map. Okay. So this is the language of local diffeomorphism. Very, very important. Very important. Now we state the inverse function theorem. Suppose omega is open subset of Rn, and F is a C1 map continuously differentiable from omega to Rn, and A is a point in omega. So this is the background of the theorem. The condition is that if the determinant of the derivative matrix, that is the Jacobian determinant, is not zero at A, then F is a local diffeomorphism at A. Using the language local diffeomorphism we just introduced. So more precisely, there are the open set containing A and another open set containing the image of A, such that F restrict to U and map to V is bijective. This is the first conclusion. Because it is bijective, 1, 2, and 1, 2, 1, it has an inverse map. The inverse map is a map from V to U. It's also continuously differentiable. So this means that this is what we say F is a local diffeomorphism at the point A. Okay. Now the inverse, this new map, that is the inverse map or inverse function of F, is C1 differentiable. Therefore, we are interested in the derivative of this map. So this is the third conclusion of the theorem. The derivative of this inverse map at every point equals the derivative of X, the inverse matrix of this X. Here, X is a point in U, and Y is Fx. Or you can say this is equivalent to X is the inverse map applying to Y. Therefore, this formula can be written in this way. Because X is precisely the inverse of F applying to Y. So this is the content, the condition and the conclusion of the inverse function theorem. Okay, we will prove this theorem using the lemmas, the open mapping lemmas we just established in the next lecture. Okay.